All right, so what we're going to look at here is how to name ionic and molecular compounds. Okay, simple kind of binary ones to start with. Okay, but then we'll start looking at ones that contain more than two things. Okay, and how we name those. So first off, what's the difference between an ionic compound and a molecular compound? Anyone remember? Sort of, yeah. I mean, we have to make sure that they have equal numbers on both sides, but they might start off not even because they're going to have something from one side of the periodic table and something from the other side. And the periodic table is divided into what, two sections basically? Metals and nonmetals. Okay, so an ionic compound has a metal and a nonmetal in it, right? So we might want to write that. Okay. So ionic compounds, okay, metals and nonmetals. Okay, whereas molecular, okay, two or more, okay, nonmetals. Which reminds me. All right, so on your periodic table, metals are on which side? On the left-hand side. Nonmetals are on the right-hand side. Okay, there's obviously more metals than there are nonmetals. Okay, for whatever reason. Okay, that's just the way it is. Okay, you'll also notice on your periodic table that there's some color codes on there. Okay, some of those elements, when we get into reactions, okay, some of the nonmetals that are highlighted there, when they're by themselves, bond with themselves, and they come as pairs, or they come in groups of 4, they come in groups of 8, depending on what they are. Okay, and we'll get to that when we get to reactions. For right now, it's not all that important. Okay, but just know that color code will come into play later. All right. So ions and ionic compounds. Okay, so ionic compounds occur when we get a metal and a nonmetal reacting to form a new molecule. Okay, and those molecules typically involve a trading or swapping of electrons. Okay, not so much a swapping, more of one giving them away and the other taking them. Okay, so in an ionic compound, both things that are involved, both elements that are involved, get something out of the reaction. Okay, what all elements want to have is they want to have their outer orbitals or outer shell filled with electrons. That makes them more stable. Okay? Most elements do not have that situation. The only elements that have that situation all the time are the noble gases, and that is the far right-hand column. So that's helium, neon, argon, krypton, xenon, and radon. Okay? They have their outer shell full, which is why we call them the noble gases. They never react with anything. Okay? Those elements never get involved in chemical reactions. They have no reason to. Their outer shell is full, and they're happy. Carson? Yes. Pardon me? Yeah, they behave very similarly. That's why they're in a group together. Okay, and that's how the periodic table works. Okay, the same properties or similar properties occur periodically. That's where the name periodic table came from. Everything in group 1 is essentially a soft, silvery metal. Okay, that reacts violently with water especially. Okay, and in the second column they react less violently. They're still soft and silvery, but they tend to be a little bit harder. Okay, so we get these patterns or periodic reoccurrences of certain properties. So anything you see that's in the same vertical column, okay, is going to have similar properties. Yeah, so everything that's a noble gas behaves similarly. Right? We can tell them apart by running an electric current through them. They glow different colors. That's how we make neon signs. Okay, you either color the glass or you change the gas that's inside, and they glow a different color. Okay, all right. So in an ionic compound, okay, metals typically want to give away their electrons. That's the quickest way to having a full outer orbital, is to give some away. All right. Most atoms, their outer shell can hold 8 electrons. All right. So for sodium, okay, sodium has how many electrons according to the periodic table here? 11. It's got 11 protons, it's got to have 11 electrons. All right. So if I'm looking at sodium, okay, here's the nucleus of sodium, okay? The first shell of electrons typically holds 2 electrons. It's not something you're really going to need to know, just for explanation purposes here. Okay? And the next shell holds 8. right? So we're up to 10 electrons now. We need another shell for that last electron that sodium has. All right. That shell can hold 8 electrons, and it only has 1 in it. Is it easier for sodium to give 1 electron away or find 7? Give 1 away. Okay? Metals are typically like that. It's easier for them to give up electrons and go back to the last shell that's full, okay, than it is to pick up enough electrons to actually fill their outer shell. All right? Everyone follow me there? Okay. Chlorine is the opposite. Okay? Chlorine, okay, according to our periodic table, has 17 electrons. So it looks like this. Here's the nucleus. Okay? The first shell has 2. The second shell has 8. And the next shell has 7. It only needs 1 more electron to fill that shell. So it's easier to find people to take 7 or give up 1. Or sorry, pick up 1, sorry. Pick up 1. All right? That's why sodium and chlorine get along so well. They each have what the other wants. Okay? Sodium wants to give up an electron and needs someone to take it. Okay? Chlorine needs 1, happy to take it. Right? So they react, we get sodium chloride. Okay? All right. Some things that happen with this now. Once sodium gives up that electron, the sodium atom has more protons than it has electrons. So it now has what kind of a charge? Positive, right? Because it's got 11 protons still, but now it only has 10 electrons, right? So it has a charge of positive 1. Chlorine, meanwhile, has picked up an extra electron and now has 18 electrons and only 17 protons. So it has a negative 1 charge. Okay? Ionic compounds, typically, once they've formed, they can be separated quite easily because they each have what they want. That sounds awful. Don't think of it from a sociological perspective. Okay, they both got what they wanted, so there's no reason to stay together anymore. Okay, don't take that from sociological. Okay, but that's essentially what happens, which is why when you drop ionic compounds in water, they typically dissolve very easily, and when they dissolve, they break up into their 2 parts. One that's negatively charged and one that's positively charged. So ionic compounds, when they're dissolved in water, will conduct electricity. Okay? Whereas molecular compounds, even if they'll dissolve, don't split into positive and negatives. There's nothing to conduct the electricity then. Okay? We'll talk about that a little more when we get to properties of compounds. All right. Is that sort of making sense there, how an ionic bond happens? An ionic bond happens because they give each other what they're looking for. Okay. For the naming parts, okay, naming ionic compounds is pretty easy. We name the metal first, we name the nonmetal second, and we change the nonmetal's ending to "ide." Okay, so we got sodium and chlorine together, that's going to be sodium chloride. Okay, we change the ending to "ide." Okay, if I'm putting magnesium and oxygen together, I'm going to have magnesium oxide. Right? If I'm putting sodium and fluorine together, I'll have sodium fluoride. Okay? If I have aluminum and sulfur together, aluminum sulfide. We always make the non-metal end in "ide." Everybody okay with that? Okay? So from that, it sounds like the rules are pretty simple, right? But sometimes it's a bit misleading if we're given the formulas. Okay? So if I put aluminum and chlorine together, I get AlCl3. All right? I still just call this aluminum chloride. Why don't I call it aluminum trichloride? It's not molecular. Molecular compounds, we have to use prefixes. We don't have to use them for ionic compounds because there's only one possible way for aluminum and chlorine to go together. Okay? Remember, they have to trade electrons. They got to balance off their charges. Aluminum has 3 electrons it wants to give away. Chlorine can only accept 1. So if aluminum wants to go together with chlorine, how many chlorine do there need to be? 3. Okay, we still have to end up with a charge of 0 for a compound to form. So aluminum wants to give up 3 electrons. That's where that whole drop and swap thing came from. You guys remember that from before? Okay, that makes the charges balance out. Okay, we take aluminum's positive 3 charge, we put it here. That means we're going to need 3 chlorines because each of them can only take 1 electron. Okay, and we put the 1, but we don't write ones. Okay, so we end up with the LCl3. Right? So that's why we don't use the prefixes in ionic compound names. If aluminum and chlorine are together, there's only one way they could go together. So we don't need to indicate how many there were. Okay? In molecular compounds, it's different. Molecular compounds don't balance charges, so they could go together in essentially any combination of numbers. That's why we use prefixes. We have to say, this is the mixture of nitrogen and oxygen that has this many nitrogens and this many oxygens, because it could be any combination. Okay. All right, questions there? All right, I want you guys, let's just do 1 through 5 for right now. Okay, I want you guys to name 1 through 5, then we'll go through those together, and then we'll try the rest. Okay, so just do 1 through 5 for right now, just writing their names out. Okay. All right, so let's have a look at these first 5 here. So I've got sodium and chlorine together. That's going to be sodium chloride. Now here's the thing that people really have trouble with. These are not proper names. As a result, they don't get what? Capital letters. It is actually incorrect to use a capital letter when naming a chemical compound, unless you are starting a sentence with it. Okay, so you should not capitalize. Okay, that's going to be a tough habit to break. Right, but you should not capitalize your names of chemical compounds. They're not a proper name like John Smith. Okay, they're a chemical designation. All right, for number 2, I've got potassium and fluorine together. So that's going to be potassium fluoride. And fluorine spelt a bunch of different ways. I never spell it the same way twice. Okay, sometimes it's OU, sometimes it's UO. Okay, you actually look on different periodic tables, it's spelled differently. Okay, all lowercase. All right, for number 3, I've got hydrogen and iodine together. So this is going to be hydrogen iodide. Now, hydrogen, metal or non-metal? Hydrogen's a metal, actually. Look where it is. Yeah, it's a gas, but it behaves metallically. It also behaves non-metallically. It only has 1 proton and 1 electron, so it actually can be either. Okay, if it's listed first, like it is in this compound, it's a metal. If it's listed anything other than first, it's behaving as a non-metal. It's one of those tricky ones that can be either one. Okay, so yeah, it's like a transgendered element. It identifies both ways. Yeah, something like that, I guess. Okay, all right. Number 4, okay, we got calcium with bromine. Okay, so I got to write this as calcium bromide. Nope, this is an ionic compound, so it doesn't get a prefix, right? This is just calcium bromide. There's only one way for calcium and bromine to go together. Okay, and of course, that's the tricky part, right? We see that 2 there, we automatically want to write a prefix for it. Ionic compounds don't get prefixes. For number 5, I've got aluminum together with astatine. So this is going to be aluminum astatide. Okay, is that making sense to everybody? All right, finish them up. I'll give you a few minutes, then we'll go through the rest. All right, let's have a look at the rest of these here. All right, so for number 6, I've got cesium with sulfur. So I'm going to have cesium sulfide. Okay, you can spell that with an F or a PH. Doesn't matter to me which way you do it. Okay. For number 7, I've got sodium with oxygen. Okay, again, it doesn't matter if there's a 2 there or not. I don't put prefixes in ionic compounds. So we've got sodium oxides. For number 8, I've got barium with selenium. Okay, so that can be barium selenide or selenamide. It doesn't matter which way you did it. Sometimes people keep more. So it can be barium selenide or selenamide. Okay, either one is fine. Okay, for number 9, I've got radium and telluride. So I'll have radium telluride. Okay, for number 10, lithium with fluorine. So that'll be lithium fluoride. Okay, for number 11, rubidium with sulfur. So rubidium sulfide. Okay, for number 12, strontium with iodine. So strontium iodide. Okay, 13, calcium and oxygen, so calcium oxide. And lastly, magnesium with selenium, so that's magnesium selenide. Okay, questions on any of those? Okay, big thing to remember is just that you don't need prefixes for these ones. Okay. Anyone need that anymore? Now, tricky thing comes into play here with some ionic compounds. This will be new. Okay, you won't have taken this before most likely. If you look at your periodic table, some of the metals have more than one possible charge. Okay, especially the ones in the middle. All right, so if you look at, let's say, iron, for example. Okay, iron is number 26, but in its box it says 26, 55.85, and then the listed charges are +3 and +2. Which means sometimes iron gives up 3 electrons, and sometimes it gives up 2. Well, this presents a problem, because two things then could have this name. That means there could be two compounds with that name. This one or this one. It depends whether iron gave up 1 electron, or sorry, gave up 2 electrons or gave up 3. Now, how confusing is it if 2 people have the same name in a class? It can be, right? I call it, especially if you're one of those people, I call your name and you're like, yeah, 2 people call, right? It can be confusing. Well, imagine you have the same first and last name. I actually had that last semester. It was the weirdest thing ever. Okay, I had 2 Chase Andersons. It was really weird. Okay, that would be the problem here. Now, it's inconvenient when it's 2 people, but let's say that this stuff is in vitamins and this stuff is highly poisonous. Okay, that's a problem, because someone says, yeah, I take this many teaspoons of iron oxide every morning. Oh, that sounds great. That guy's really healthy. I'll eat that and you die. Okay, well, that's a bit of a problem. We've got to have a way to tell these 2 compounds apart. Right? What we do then is we put in their name a Roman numeral that tells us which form of iron was used, the one that gives up 2 electrons or the one that gives up 3 electrons. Right? How am I going to tell which one was which, though? You got to look at the charges. Okay? If I'm dealing with this formula here, remember that all compounds, their charges have to add up to what? They have to add up to 0. So the number of negatives has to equal the number of positives. All right, on your periodic table, what is the charge on oxygen? -2. It's always -2. There's no non-metals with more than one possible charge. Okay, so I look at the non-metal, I see that oxygen is -2, and there's only one oxygen here. How many irons are there here? Just one. So what iron is this if I'm going to have the charges add up to 0? +2. Okay, everybody follow me there? So I was able to figure out that this is iron Roman numeral 2 oxide. For this one, okay, it's the same idea. Oxygen is always -2, but how many oxygens do I have? Okay, so how many negative charges? -6. All right, that means I need to get 6 positives out of these 2 irons. So this charge on iron has to be 3. +3 times 2 is +6. Whichever one you got to use to get them to work out, that's the Roman numeral you're going to write down. Okay, so you're going to be using those charges a little bit. Okay, you're kind of doing the swap and drop in reverse a little bit. Okay, is essentially what you're doing. Don't always just go like this and go, oh, well, there's a 3 here, so that was a 3, because it doesn't work every time. We'll talk about those times tomorrow.